Alright, I'm going to go through this paper that myself and Kirsty wrote for the Learning, Analytics and Knowledge Conference for 2025 on game theoretic models of intangible learning data. Now, as a bit of a backgrounder of why this paper came into existence, it kind of stems from the fact that my background sits in two worlds. One side is sort of the modelling, the statistics and the understanding of data. But then the other side is from spending 12 years in classrooms across 3 different continents and having a feel for what learning looks like in a range of contexts. And so every time I'm sort of analysing things, I've got this burning question around, is the data that we're seeing in these learning systems and extracting from them genuinely representative of the learning processes? And I keep coming back to this, and it's something that the field of learning analytics has worked really hard to sort of identify and work with in terms of trying to work out if what we're doing is aligning with these learning processes. Also, if we're confusing sometimes the outcomes and learning and how we're measuring them, and highlighting ways we might move forward in this as well. So, acknowledging that missing data and what we can't see is really, really important to the kind of inferences we can make. And does a lot of work in terms of doing this, where we sort of impute data with where we've got some of the same thing and it's just got missing and like that. Or if we've got related things, we can model them, such as with latent variables. But there's still this burning issue that critical aspects of learning may always be intangible. They're important to learning, but we may never be able to measure them, certainly not directly. And we can get close, and there's even been lots of work doing this within the field just in this conference where this paper was, addressing intangible things like curiosity, intention, confusion, and trying to work out the best way that we can get a good proxy for that. This paper is sort of going in a different angle. Rather than looking at the data we do have, it's trying to build a mathematical model to explain or at least explore what's going on with the hidden learning process. The framework it's building on is one called evolutionary game theory. Now, game theory, so without the evolution, is the understanding and analysing games played between players. But what's really important in the context of education is that this is studying decision-making process, and a decision-making process is a hidden cognitive thing that we can't really get a precise measurement on directly. And the evolutionary game theory part of it looks at this collection of processes or decisions that people are making with numerous agents, such as a classroom full of students, and how those strategies evolve over time. If you're used to going from data with your models into some kind of inference, this will require a little bit of a different way of thinking. So I'd just like to highlight here, I'm not going to answer this at this stage, but just prep you, if that's what you're sort of used to, making inferences from data, that this is a different way of thinking and it requires a different frame of reference. I'll highlight when that comes into play. So the question the paper tries to address is this one here. How can game theoretic models connect intangible data to the data we have available in learning analytics? The process we go through is sort of describing what we can, at the scale we can, formalizing that in mathematics so that we can then model that and simulate it and calculate things based on it in a range of environments, and then collect that together to try and connect to the things that we might be able to observe. The model itself builds on some earlier work. There has been a bit of work with game theory in education, not much, but over a big period of time, maybe even 50 years. But this particular model is about peer-to-peer learning, so support and feedback, where there is this tension between how much effort you put in. So the effort you're putting into is something that's not essentially your own, but is going to help other people. So you've got this tension between being cooperative or free riding. Now, the game. We start off with 2 students who have done some work. They then have to review each other's work and have to decide how much effort to put in. Now, this decision that they make is a hidden cognitive process that we cannot observe. So it's really hard to work out effort, even self-report of effort. It's hard to be honest with yourself about how much effort you've put into something. Once they do this, they share the feedback with each other, and we can start formalizing what's going on here. So they incur a cost. That was the effort they put in, and that's what we say is their strategy. This paper explores sort of like 3 tiers of cost, like cooperator, which is applying full effort, token effort, which is half, and free rider, which is assigned 0 effort, but you can imagine it as like sort of negligible effort, like you've just put like some smiley faces and some ticks on there. That can be extended to a continuous scale with the model that's presented here as well. So once they've done that, they get some perceived value. That value is dependent on how much effort the other person put in. They also get some perceived value from the effort they put in themselves. You can imagine that is like assigning, I've done this work in providing feedback to someone else. I actually got something out of that. Maybe it doesn't go towards my work that I'm doing at the moment, but maybe it taught me something as well. Maybe even there are marks assigned to this process, but I get some effort to myself from providing the feedback. We then assign numbers to this. So F here is sort of the proportion of value you would get from receiving that feedback. B is the proportion of value you get from providing the feedback. And C is the cost. Now, these numbers are made up, okay? Then there's no units here. C doesn't mean anything. But what's important is the ratio of them, and also when we explore a range of them, what happens. If we use those particular numbers, we then get this scenario called which is a prisoner's dilemma, where we can assign values to, okay, if a cooperator meets a cooperator, they get 4 units of whatever we want to call this. However, if a cooperator meets a free rider, they actually lose 2 units. Now, that's because they've put in effort, but they haven't really got much back from the other person. Now, however, if a free rider meets a cooperator, they get a huge benefit there. They get 5, slightly more. Now, the dilemma here, which is where the prisoner's dilemma comes in, is that in the overall system, you would want more cooperators. Cooperators meeting cooperators is good. You get sort of 4 on average between everyone. However, free riders meeting free riders is bad overall. You're getting 1s there all the time, a lot less than the 4. And then on average, the other one, sort of on the other diagonal there, you're getting sort of an average of 3. Okay, so you want a population, in terms of a classroom perspective, you want a population of cooperators. However, from an individual perspective, it's much more valuable for you to free ride. And this is where the dilemma and the tension comes in between. You know, not putting in the effort into a collaborative task, or collaborating and thinking about the whole. So we then analyse lots of these situations. We don't just do one game, we simulate or put it through an analysis process where we look at what happens when we have lots and lots of games. And then after each game, the students will make a decision about how much effort to put in next time based on their experience of last time. And that will change the distribution of strategies that we see used in our population. So to visualize that, we've got these little triads between cooperator, token effort, and free rider. The dot in the middle there just means we've got an even balance of those strategies in use in our population. So, like, say there were 9 students in our class, and we were representing this, we'd represent a dot in the middle. But say they share all their feedback and the cooperators go, hang on a second, I don't know if this is worth me putting in much effort. They might change their strategies next time and move over to the free rider strategy. And you would see our little center of mass move from that central point inside the triangle down more towards the free rider one. Okay, so that's the movement of the strategies, but what we're really interested in is not how many are in each spot, but it's rather the movement that we would expect to see along with those parameter conditions. So those two together, the movements along with the system parameters, that is our reference frame for how we're going to make inferences. So once we do that, we can look at all of those movements together. And here we see sort of a scenario where the conditions are that the cost is sort of about twice the benefit to yourself. In this case, you see the strategies would move, if they're in the center at least, if they would move sort of down away from the cooperative strategy and be pulled towards the free riding strategy. You can see the blue areas are kind of like wells. These are areas where you would expect to see not many strategies change. So in that case, we may not see much movement if we have a whole bunch of cooperators, at least in the short term, because people tend to stick to their strategy, even because it might be a slight disadvantage to some free riders or token efforts. But let's say you get an influx of free riders or token efforts, then it would start to move away from that cooperative strategy. We can, though, change the environmental parameters a bit. And you can imagine this might be around, like, let's say we assign marks to the doing of the peer feedback, in which case we're adding some perceived value to the peer feedback. Maybe you just remind students every day that you learn lots from providing feedback to others. You change the perceived value of it. And in that case, our movement of strategies changes. We now move up and away towards the cooperative strategy. We can then explore a range of these a range of these environmental parameters and explore what's happened. And we can see that, you know, as the self-benefit decreases, we get pulled more and more towards that bottom free riding corner. And as it's a bit more balanced, you can see there are more of these wells appearing where the bluer regions are a little bit more stable, and you would find the strategies just sort of sitting there. As the difference gets more extreme, we get really dragged more and more, which kind of makes intuitive sense about what would happen. But this really is just looking at this one ratio between cost and self-benefit. We can then play a little bit more. So one of the great things about this kind of modelling, despite it being quite a dumb and simple model, is that we can imagine data that hasn't even occurred yet, or situations that haven't happened. And so, for instance, we can imagine, okay, we've got large language models coming in. People start using Gen AI to support the feedback they're providing to other people's. So we can see that this can be incorporated into our model. We can have a parameter in there around the extent of the Gen AI use. It'll have these factors of how it's changing these things, but then we can play with those parameters and see what happens to the system dynamics. So here we've got high self-benefit scenario, but Gen AI use has come in quite a bit. I think this is full, so everyone's using it. Now, again, we are still moving towards the cooperating strategy, but notice that this has dampened the movement quite a lot. We have much more of these blue cooler zones where we would expect sort of stable groups of students, like student populations, and not much movement. So whatever, you can imagine this is like, say we've been putting lots and lots of effort into promoting cooperative behaviour. The introduction of Gen AI here would seemingly dampen the movement towards that cooperative strategy. We can then explore like a whole range of values here, and you can see that sort of damping there. But you can also see that when the Gen AI use is high and the self-benefit drops, it's still quite dampened. So a little sort of intuitive feel in the inferences we might make from this model, to the extent we believe it, is that we would expect the introduction of Gen AI usage in these situations to dampen any kind of effect, either negative or positive, towards cooperation or free riding. Now, we need to connect that to the data that we might observe. So we've got the change in cooperation. We might be able to see that. Even if we can't measure it precisely, we might be able to get a feel of, are these students cooperating more at the beginning or the end of the period of study? We might also see the change in the overall impact of cooperation. So that's the sort of average value that we expect in the classroom, how that's changing over time. So we might get a feel for the quality of work coming through after each feedback iteration. We may not be able to measure it precisely, but we might be able to get a sense of the change. We might be able to get a sense of the change in Gen AI use through tools to try and measure it, but we also might just hear word of mouth and try and know what's going on. What we can do now, and what we've done here, is looking at those little three metrics from a range of simulations across a range of parameters that seem to be encapsulate the kind of movements we'd expect, we can make a distribution of that data. Now, notice that even though we sort of varied the parameters over a whole range of spaces, we still only get sort of like a narrow set of distribution here. We're not getting a big, wide plot covering everything here. We see some regions don't tend to occur, even though we don't know much about it. We don't seem to see, like this big blank area in the top left, we don't seem to see a change in the overall feedback value in conjunction with a drop in cooperation. That's just not, even with the Gen AI coming in and changing things around, that's not something that we would expect to see. Again, like how you would connect this to data is a bit up in the air still, but this is a distribution. If you don't know something, this could be provided as a prior distribution in a Bayesian model framework, particularly when you have a complete lack of insight at the beginning. This might provide at least a broad prior that you could use in some other modeling framework. The other way to think of it is kind of what I've been talking through now, is sort of connecting it more to qualitative insights. So like we might see this, describe that in words, go to people and find out, is that what you are seeing? Is that what you're expecting? That kind of thing. So even though this is a very sort of numeric, numbers-based simulation coming from a mathematical world, it may be better to connect this to qualitative data rather than quantitative. But that's for further work. If anyone wants to do it, I'm also very keen to do it. So what have we done? We've described what we can with learning between two students mathematically, so that we can then use this to model a range of scenarios and collect those results together to form a data distribution, which we might be able to use elsewhere. Just to be clear, we're not making claims about what's going to happen in the future with cooperation and Gen AI. This is more of a proof of concept to show one way that we might be able to see into the unknown, into these hidden processes that we find all the time in learning and learning environments, even without any data. That's the end. I'm just going to go through a couple of questions I got at the talk though, because I thought they were really good. One was around the connection to data, and that was why I was highlighting before that I think it's more natural to connect this to qualitative data, which does seem strange for numeric-based things, but also that the modeling can connect through a Bayesian framework as well. In terms of the belief in the model, like, even though I'm not making a claim about the Gen AI here thing, I do feel like at least my intuition about the dampening effect, like maybe this will support situations where we didn't have much cooperation, like a massive online course where there's not much human connection. Maybe the introduction of supports to help people do the peer feedback might increase a little bit of cooperation gradually. And maybe if we put a lot of effort in and we've got these cooperative environments, maybe it would dampen it. I'm not as sure about that, but I do feel like it fits a little bit around my intuitions there as well. And the last question was about adding aspects to the model. So like incorporating something like the academic level of the students, like say one's way far ahead, like 3 years ahead of the other one, they may not get the same value. I mean, that can be added, and you can add sort of a whole bunch of things to this. You've always just got to balance up the addition of extra structure and parameters with how much meaning you'll get out of it, because every time you add an extra thing here, you've got more parameters to explore and more things to do, and it gets more complicated. So it's a real balance between parsimony and detail and precision. Alright, that is it. There is the paper and the code if you would like to see. Any questions, please do reach out.